So good evening, and tonight's discussion will be about Martian auroras. There's been some corroboration of information to observe them. They're actually in ultraviolet, not invisible light. So that was one of the reasons why they hadn't really noticed them before, but we'll get into that later. First, let's do the news. So for those that stay up late at 2 a.m. on Monday, August 2nd, Saturn will be at closest approach, which is not too many hours off of opposition. They're kind of close together. So if you want to see Saturn at its brightest and largest for the next couple of years, it'll be early morning Monday. And as they always like to confirm whatever Einstein predicted, they've detected X-rays coming from around a black hole, bent by the gravity of the black hole. And ignore this artist rendering. That was not actually what they observed. So what they did do is they looked at a black hole named Zwicky 1. It's about 100 million light years from Earth. And the black hole normally has its own jets that are, in the case of this one, pointed towards us where we can pick them up. But they actually detected X-rays that weren't from the black hole. They were from around the rim of the black hole. And they detected these using 2 orbiting satellites. The first satellite that they used was the NASA NuSTAR. It's an X-ray satellite. And the other one is the European Space Agency's XMM Newton. So that's another X-ray satellite. So they both together made these observations, and that allowed them to confirm what each other saw. And what they saw was X-rays that, because of the angle, could not have been coming from the black hole. They had to be coming around the black hole, which sounds like a discovery. It was predicted that, the gravity of a black hole is very sizable and will bend even light rays. Well, X-rays happen to be very high energy light rays. They're still photons. So it bent the photons and they detected them. The parts that they didn't get into was X-rays from where. So they don't know the source of the X-rays behind the black hole, but they know that the X-rays came from around the edge of the black hole, because the high energy telescopes are fairly narrow field of view, so they can look at the edge of a black hole. So on Tuesday, as opposed to yesterday, Boeing will attempt to launch their Starliner orbital test flight number 2, second time try, to the International Space Station. This is an uncrewed, unmanned capsule. And I provided both the sort of space.com link, so you can see some pretty pictures of it, and as well as the Boeing marketing site. If I can get there we go. So you can actually see what it looks like, all painted up, pretty colors for you not to be able to notice those colors in space. But the first time they did this, the second stage didn't quite fire properly, and it didn't get the boost that would take it up to the International Space Station. And since there was nobody on board and they couldn't quite get it to do what they wanted it to do, they just dove it back in and burned it up. This one is supposed to make it up to the International Space Station, autonomously dock with the ISS, and then hang around for a while and eventually leave. And I don't know if it's coming back or it's burning up. They haven't said that yet, but it's not going to return with people on board because it's not at that stage yet. If you remember SpaceX, when they were doing the Dragon capsules, they actually had to fly 2 Dragon capsules, one mission and then another mission unmanned to the ISS to prove they could do it, because the first time they didn't believe they could do it because it was successful and it worked and it didn't have any side effects. And do it again. We don't believe you did it the first time, but they did do it the first time. They did it the second time. And since then they've had 2 crewed capsules, 2 Dragons with people on board. The first one had 2 astronauts. The second one had 4 astronauts. So Boeing is in about a 1.5 year delayed catch-up mode. So that will be another commercial capsule that can make it to the ISS. That's their hope. And speaking of commercial competitors, the Government Accounting Office, the GAO, was requested to make a ruling. Blue Origin and another company called Dynetics, not Dianetics, but Dynetics, was claiming that SpaceX should not win the contract for the lunar lander because it had already been given to Blue Origin. But Blue Origin has already missed 2 years worth of contract deadlines. And so NASA said, why should we give it to you? We're going to give it to somebody who actually has launchable spacecraft and has proven they can send people up and get them down safely. If you remember, Blue Origin's recent flight was suborbital. They just went up and then came back down. It never actually went into orbit. Well, SpaceX is quite a bit farther along than that. So NASA said, we're going to take the contract away from Blue Origin and give it to SpaceX. And, Blue Origin did not like that. But the Government Accounting Office was solicited by NASA to say, could you please claim from the government's perspective, what is the correct approach here? And the GAO said, given the information that we see and what NASA is trying to achieve and when they're trying to achieve it, and the fact that you other lot aren't meeting your existing deadlines, I think that NASA has every right to give it to, a winning solution. So GAO sides with SpaceX.
That does seem appropriate.
Well, you remember in the last few weeks, I've been talking about United Launch Alliance.
Breach of contract.
And the Space Launch Agency, and both of them have already missed contract windows that, allowed the contracts to be given to SpaceX. And they don't like that. Well, if you don't like it, get on the ball, get to where you need to be. But, they can only do so much so fast because they have a different business approach than SpaceX does. People like watching things blow up with SpaceX, but they learn a lot from that. And the second time they do it, they generally don't have the same failure. So they're progressively moving to things that work. And speaking of things that don't work, Russia, after several years, finally launched their addition to the International Space Station. After having threatened to leave the space station, they launched, another module to the space station. So they removed a docking port and they put in their Nauka, N-A-U-K-A module, and they saved the module. They drained off the excess helium pressurization fuel because helium can have problems. So they thought they were safe doing that. But shortly after they did that, and after this module was physically connected to the space station, it decided, oh, I need to turn my rocket thrusters on. And it promptly tilted the space station 45 degrees. And the space station went, I'm not in the right position. And it turned on the thrusters on the other Russian capsule to counter it. So you had 2 Russian capsules on each side of the ISS fighting against each other. And my thought was, gee, the space station must be pretty sturdy across the main bus. Otherwise, it would have broken in half. But it didn't. Everything's fine. They found the source of the problem to be a software bug. So ignore the fact that they had a software bug that almost ripped the space station in half, but that's okay. So the next problem they had with the Russian module is, hey, look, they have a leak. Apparently, they didn't successfully pressure test it on the ground. So they sent it up to orbit, they docked it, they sealed it up, they applied the normal internal pressure with the external pressure of vacuum, and it started to leak. So now they're set about finding the leak. If you remember, there was also a previous Russian module that had a leak, and they found out that some unscrupulous individual had drilled a hole, a little tiny hole, through the outside into the inside, and you couldn't see the hole on the inside. You had to go on the outside and see the hole because it sort of leaked around the wall. So they're gonna have to find the leak again because, hey, they got another leak. Luckily, they can seal it off. So if that particular module, loses pressure and it's not habitable anymore, they can solve it. This is not the first leak they've had to deal with. Yesterday, on Friday, they launched an Ariane 5 rocket. That's one of the largest Ariane vehicles they have launched from French Guiana in South America. They launched 2 satellites. So this is the largest rocket that they have in the Ariane class. You can see the 2 solid side boosters on it, plus the central rocket. And they launched, count them, 2 satellites. SpaceX launches a much smaller Falcon 9 and launches 60 satellites because the individual satellites are much smaller and they fold up into a more compact package, and they use ion propulsion to make the engines smaller to take them up into their orbital position. But these are old style satellites. They're built by Airbus over in Europe. And the 2 satellites are, one is Embratel Star 1 for Brazil. That satellite weighs 6,190 kilograms. For those of you in poundage, that satellite weighs 13,650 pounds. One satellite.
The sad thing is that the Brazil has a launch system that is even near to the equator,
Yes.
but they are not using anymore because they remove all the funding for science.
Well, the other thing is these 2 satellites are being launched to geostationary orbit, and the Brazilian rocket complex does not have a rocket capable of taking this much mass to geostationary orbit. So
Yeah, they don't have the rocket, but the facility is capable of.
Well, the launch pad is capable of it, but they don't have a rocket for it. So Brazil let it all out to French Guiana to launch it. Now, the other satellite that was launched is from a company called Eutelsat. This is a European consortium of satellite service providers. They're private satellite services. And they launched a satellite, a new one. This is their first of their cookie cutter class satellites. These are called software defined satellites. Instead of building a unique satellite for each mission, the idea is to build one base framework of satellite that you load different software onto. You maybe attach different instruments, different antennas, but the baseline satellite, you don't have to keep redesigning for every satellite you launch. So I think of it as cookie cutter satellites. That satellite weighed 3,461 kilograms or 7,630 pounds. A SpaceX Starlink satellite weighs in at 530 pounds. So when you talk about big satellites that are going to have huge solar panels and large parabolic dishes that are going to reflect the sunlight, you're not talking about SpaceX Starlink satellites. You're talking about these kinds of satellites. But nobody makes any comment about these. We're going to take the largest rocket that Ariane has and lift 2 satellites.
I like the video that was sent out last week that you had us look at. I got a chance to review it, and it was about a stellar
explosions. Yeah.
What?
Stellar explosions was last week.
Yeah, but I'm talking about the news articles. You sent us some videos, and one of the videos was regarding the oil rigs, how they're launching oil rigs.
I found that interesting too. I had already.
That was amazing.
When we were covering commercial U.S. spaceports, I talked about SpaceX buying up oil rigs, but I couldn't get into the detail of what modifications they have to make to them. So this guy's video, he went down into the deep technical dive of you basically starting with a platform with some struts because you have to strip it down to the bare bones and then put everything back on top of it.
It was beautiful how he did that. And he did it in a way that didn't make you feel that it made you feel intelligent and that you could follow what he was talking about. And the best, I really like the last part too, where they showed all those small satellites that are around the world and how they're linking together and how that's going to help the world. It was very nicely done.
Well, you're going to want to look at one of the satellite companies that I mentioned today. They actually have satellites that are going to be low Earth orbiting, and then they have geostationary, and they don't have that many ground stations. So they're actually putting different radio frequency communication links from the low ones to the high ones to get down to the ground stations. Instead of doing that, SpaceX actually has satellites at multiple levels, and the satellites are interlinked on a real-time basis with lasers. So they don't even use radio waves. So people are always talking about the radio interference pollution of satellites, and SpaceX is not even going to be using that. They're going to be using lasers to connect them. And they're not visible lasers, they're invisible lasers. So, but it's, you know, where the light is as opposed to where reality is.
And when they get done linking them, then there'll be ability to have Wi-Fi everywhere.
Yeah, the Eutelsat is actually going to be doing 5G backbone. So if there's a 5G antenna sitting in the middle of rural nowhere in some other country, that will link up to the low-flying satellite to give it its connectivity. And it'll switch between different satellites as they go crisscrossing overhead. SpaceX kind of cuts out the middleman and says, if you put one of our pizza box sized dishes up on the roof of a building, we give you a router with it, and you can do Wi-Fi or wired routers fan out from that. So that doesn't require you to put in a cell phone tower where you're going to do this, and you get direct high-speed internet at 150 megabits, but it doesn't give you cell phones. So that's what Eutelsat is saying, is have somebody go in there and put your cell phone service in, because that's where the money is to be made. And then that tower will link up to our satellites to avoid the cell phone company having to build infrastructure on the ground to link the towers together.
So they did refer to cell phones somewhere in that presentation, and that they hoped in the future that this would make it so that the cost of doing phones would decrease.
Yes. If you've ever studied how cell phone networks grow out in these rural areas, they'll put a tower in at a place that has backbone access. And then they'll put another tower, 5 miles away, and it'll actually link the towers wirelessly. They'll actually do if you've ever noticed a cell phone tower that has what looks like a round dish antenna on it, that's got a cover over it, that's actually linking that tower to another tower, because they didn't want to have to run fiber optic cable between the two towers.
I see.
Okay. So the Japanese Space Agency has found, using infrared observing, using their own satellites for infrared observing, 2 of them, unusually red objects in the asteroid belt. And the asteroid belt doesn't have unusually red objects. What does have is trans-Neptunians, the stuff that's on the Kuiper belt past Neptune. Those tend to be redder. So what they're postulating is that maybe these 2 reddish objects in the asteroid belt actually formed out as trans-Neptunian objects in the Kuiper belt, and through some reason, they migrated inward to the asteroid belt. Of course, that's all postulation. They weren't there at the time to see it happen. But that means that there had to be a large gravitational object that would sling them inwards, which once again, puts forth is there another giant planet out there beyond Neptune that would have the gravity that would perturb these 2 to, spit them inwards? Someday we'll find it. Once again, it's in the category of stay calm and carry on. The largest known comet, which is over 100 miles across, 150 kilometers, is Bertinelli Bernstein. It won't be anywhere near the Earth until 2031. And it's still not expected to be a threat of impact to the Earth. but you may see it as a naked eye visible comet if everything works out properly, but not until 2030 or so.
Oh, there it is.
Yeah, now it loaded. Of course, that's an artist rendering. We don't actually have an image of it. It's out a little closer than Saturn right now. So it's way out there, you know, it's magnitude 16. So you're not even going to see it with your amateur telescope. But give it until about 2030 and then you can take a look for it.
Did they that photometric data from Hubble, I think. That's why you can see some of the bumps. This is most likely looking like a photometric data from Hubble.
No, I know that's an artist rendering.
Okay.
Yeah, that when you see all the other debris around it and you see how close the debris is, you know, it's Star Wars meteor field closeness as opposed to real world massive separation between the individual asteroids.
Right.
You know, that's got to be an artist render. Okay,
And
that's all I had for the news. Posted the video from last week, which was stellar explosions or things that go bang but not big bang. Oh, and it ended this week. The American Astronomy, American Astronomical Society. This is a group of professional astronomers. They're very much against constellation satellites. They think it's going to destroy all visible astronomy observing forever. So they love to take pictures of when Starlink satellites are moving to their destinations and they're still flying in formation and they're brighter. They like to take, you know, 3-minute exposures directly in front of some bright object like a star and say, see, we cannot observe this star because of all these little white lines. Look at how overly exposed the star is. If they were actually doing observations of that star, they would never have an exposure that long. But it looks good because then the satellites become visible. If they did a normal stellar exposure, the Starlink satellites wouldn't even be visible.
Yeah.
But they've had their discussion. They did their discussion this week. It's SatCon 2. I like how it's SatCon 2, like it's a con. So I look forward to whatever their report is. You know, I don't expect them to mention China, India, or Russia, who are also putting up their own multiple thousand satellite constellations, which are satellites that are all bigger than SpaceX's Starlink satellites. And they don't attend these meetings. So any issue with reflectivity or radio, you know, noise interference, they're just not even a part of the program. But SpaceX does attend these things. Then you've also got the other corporations, OneWeb, Inmarsat, and Intelsat. So they're launching bigger and brighter things, and they're launching them to higher orbits and geostationary, which, think about geostationary for a moment. If you have a large, bright geostationary satellite, it's just going to sit there in your field of view forever. It's not going anywhere because it's always in the same fixed spot overhead. So if somebody parks one of those things near to where an observatory is, every sunrise and every sunset, you're going to have that glowing orb. But Starlink's the evil one, I guess. So today and tomorrow, I'm attending the Society of Amateur Radio Astronomers Eastern Conference. And their conferences have gone 100% virtual, as they say. So they're online. They normally do them face-to-face. The Western Conference takes place at the Very Large Array. They finagle arrangements for us to meet out there. And the Eastern Conference takes place at Green Bank in Virginia. So we don't get to look at the big toy. But I won something in the raffle today. I won a t-shirt with their logo on it. So if you see me on a Saturday evening wearing something that says SARA on it, that's my t-shirt. I have no idea what color it's coming in. But if I went to buy one of their t-shirts, it's $20.
Well, congratulations.
It cost $20 to go to the meeting. So it broke even.
That was nice.
Yep. They've had a change in leadership at the Denver Astronomical Society. A couple of months ago, they elected new officers, and they decided to move their monthly meetings from Friday nights to Saturday nights at 9 p.m. Eastern time.
Oh, oh,
So
oh.
I guess I won't be attending their monthly meetings. So they'll lose my $20 for my annual membership in November. There's no word back yet from the county parks or the county STEAM team as to when astronomical public outreach is going to be occurring again. I guess the latest return to wearing masks in public has gotten them all stirred up and they're having to, reanalyze whatever they were going to do in September. But there was at least one park that was saying, we're going to have you back here in September. And I know a lot of us aren't looking at Facebook, but Broward County Library did their Creation Station monthly video of myself and another person, Jasmine Singh, who's actually an intern for NASA's James Webb program out of Goddard Space Flight Center. So she didn't know what, that I was going to be holding a session later this year on the James Webb. And I didn't know she was an intern assigned to Goddard. So we found this out during the interview and we started geeking out technically with each other. And Bob, the host, had to draw things back. But we may see Jasmine. I told her she's very much into SETI. So I told her to go out and take a look at the Stop Looking for ET video. So I'm expecting to hear comments back from her about it. And I'm in email communication with the Space Telescope Science Institute. These are the people that are the operational management for the Hubble Space Telescope and have already been awarded the contract for operational management of the Webb telescope. They're actually going to be coordinating the public events following the launch of the Webb telescope. So we went from a technical lead at Goddard Space Flight Center to a promotional lead at Goddard Space Flight Center to now a promotional lead at STSCI. I'm waiting for eventually the janitor is going to pick this up. I don't know. We keep getting, I know what it is. We sound like we know what we're talking about already. So we don't need all of the hand holding that I'm sure the 499 other James Webb presenters might need. Later in August, I'll be sending the draft of the presentation to them for them to have a comment on it. And I've already warned them it's going to be a lot deeper technical dive than the other presenters are going to have. I'm hoping that they'll either draw information from the presentation and add it to their frequently asked questions, or maybe if we're really lucky, once I post it on the Broward Astronomy YouTube site, NASA will refer to it as, okay, if you want more than our presentations give you, here's a deeper dive, because I've actually been reading the Webb operational manual. So if you are a professional astronomer and you wanted to know about the instruments on board the Webb and how they function and what kind of science you do and how you form a request, I put my shoes in that role and said, okay, I want to use the Webb. What instruments do I have at my disposal? What are the specifications of them? What can they see? Can't they see? So a lot of that information will be brought to the presentation that we'll be giving probably in early November, since the current launch date is Happy Halloween, October 31st. French Guiana launch site is already saying that because of other things going on, they may have to delay the launch by a week or so. Nothing wrong with the launch vehicle itself. It's operational infrastructure stuff at the launch pad. I think they kind of snuck that Ariane 5 launch in yesterday. That wasn't on the original schedule, and that pushed everything out a week or so. It'll launch when it launches. I'll be happy when it does. So any comments or questions about this week's news items, or any news items that I missed? Okay, here's a technical item that I noticed that I haven't seen the backstory on yet. When they moved the Boeing launch from yesterday to Tuesday, today they moved the launch platform back from the gantry, which is usually indicative of something's not right and they have to make the decision as to whether to sort of bring it back into the shop. So we shall see what they do. Okay, and that is the news. So tonight's presentation is on Martian auroras. A few weeks back, I saw the observational data that they had detected auroras on Mars, but the auroras were not visible, which is why we hadn't seen them up until now. But apparently one NASA spacecraft did, and now we've got a second spacecraft that seemed to corroborate it. So it's kind of inescapable confirmed observations. So I said, well, let me go do a deep dive on the Martian auroras and see what they're all about and how this might change our perspective on what can and what cannot generate an aurora. Okay, so welcome. Tonight's discussion will be about Martian auroras. So what is an aurora? Well, for those of us that live closer to the equator, we've never naked eye seen an aurora. So we have to have a little explanation as to what they are. These are natural phenomena. They're not the man-made, lights in the sky like lasers and searchlights. They're eerie, mysterious, glowing and swirling lights, but you have to be in the high northern or low southern latitudes in order to see them. If you want a basic understanding, the NASA Space Place, which is an excellent place for kids to go and learn about space and science and rockets and such. They have an article there on what is an aurora. So Earth has auroras. How, why, where are, what about Earth auroras? Well, the Earth has a very hot, molten, metallic, rotating core. And when you take something metallic and you rotate it, you typically see a magnetic field. So because of our molten core rotating, we have a magnetic field that encompasses the Earth. It's weak. It's not enormously strong, but it's definitely there and measurable. Much like any other magnet, it has north and south poles. These poles are not exactly lined up with the north and south poles of rotation, and they're actually moving away from them, but they're kind of in the proximity of it. There's a north pole and a south pole. Whenever the sun has a coronal mass ejection, these are energetic particles being carried away from the sun in the solar wind, they travel along these magnetic field lines to the north and south poles of the Earth. And we have two auroras, the Aurora Borealis, that's the north one, and the Aurora Australis, which is the southern aurora. These particles from the sun travel along those magnetic field lines and they excite the gas atoms in the upper atmosphere. This is what produces the light. As you apply energy to an atom and it produces photons, and based upon the particular elements and the amount of energy applied, this determines the color of the photons. It is very typical to see a green aurora, but if you get the right energy levels, you can also get a red aurora. Yeah, you need a lot more energy for that. And the red aurora and the green aurora are both different emission spectra of oxygen. If you ever see a blue or purple aurora, those are emission spectral lines from nitrogen. So energy elements gives you colors. Here's the picture from the NASA Space Place. It kind of says it all in one picture. Obviously, it's not to scale, but you have a solar flare occurring on the sun. It results in an ejection of plasma, energetic particles from the sun. They move across the interspace medium from the sun to the Earth. Obviously, we're missing Mercury and Venus in the middle here, but they wind up hitting the magnetic field lines of the Earth, and it draws them down, much like iron filings are drawn to the poles of a bar magnet. So these energetic particles are drawn down into the northern and southern centers of the field, and that's how we get auroras. So NASA launched these two satellites. Can you see the video?
It can help you find the bathroom when you need it.
Do you actually see the video movie?
Yes, yes, perfect.
Yes, I chose, it's not actually a video, it's an animated GIF. So those display directly without sharing it for video. So anyway, NASA launched 2 satellites, stereo A and B. A is for ahead and B is for behind. They're launched in the same orbit as the Earth around the sun. So they don't orbit the Earth. They actually orbit the sun just like the Earth does. One of them was moving faster than the Earth in the Earth orbit, and the other one was moving slower than the Earth in the Earth orbit. Not by much. It took several months, but when the 2 satellites drifted around the orbit of the Earth, so the Earth, and then you had one satellite out in front of the Earth, another satellite behind the Earth, and they were both looking at the sun from different angles, you could now get stereo vision. So that's why they called them stereo. So you could detect the direction that the coronal mass ejection was moving. You could detect how big it was because you had a scale reference, and then whether or not it's expanding as it moves away, or if it gets to a certain size when it leaves the sun and then maintains that size.
So Monroe, are you saying that black dot that we see a circle within a circle? I don't know what that white.
The black dot in the center is called a coronagraph. It is a black metal disc that obscures the light from the sun. Otherwise, you couldn't see any of this because the sun would be a big bright thing in the middle that threw off your exposure.
So it's looking at the sun.
Yeah.
So you are staring at the sun, but the sun itself has been blotted out. And what you see is an ejection of plasma from the sun. That's the thing coming off the left.
Oh my
So
God.
if you imagine analogy to that is like when you try to look at like a lamp in your house that doesn't have the cover, like an abajur or something, you know, a lamp in your house. If you remove the top and you see just the bulb, you can't see much because that light just throws your eyes in, and it's too bright. And then normally you put your hand to cover it just to help out so you can see around. So that's basic stat. It's like you're holding a hand not to look at the sun directly so you can see around.
This is also a good example of how improper lighting is for light pollution. So if you have a bright light where you can actually see the light bulb, that's a bad light. And the reason why it's a bad light is you can't see anything around the light. All you can see is the light bulb. So when you put those glass coach lights with the exposed filaments on the front of your house to light up the front of your house, you can see the coach lights, but you can't see the front of the house because your eye goes bright and it, you know, adjusts the exposure, and now all you can see is the bright, and you can't see anything dark around the front of your house. So this is a good example of why you want a shield on a bright light so you can see everything around it. So a couple of things to note here. One is look towards the top at the little white dots moving. Those are background stars.
Okay, that's nice.
The other thing to notice is at about 7 to 8 o'clock, you see what looks like a hair, this round thing on the lens. That's actually radiation damage to the satellite. It's kind of like a burned in spot on the outside of the lens. So that's, you know, just what the telescope suffers from. These telescopes went up in 2006. In 2014, we lost communication with stereo B. This was the behind. Stereo A, we actually lost communication with it in 2015. Think of it as one of these satellites was moving slower than the Earth in the Earth's orbit, and the other was moving faster. Well, ultimately, what's going to happen is these 2 satellites are going to wind up going behind the sun. And the Earth is going to be on the other side of the sun, and we lose contact with them. Well, when stereo B did that, we never picked it up on the other side. Don't know what happened to it. It may actually be out there going, please, Earth, talk to me. And it's just pointed in the wrong direction. Stereo A, however, we lost communication with it for 3 months as it went around the backside of the sun. but we picked it up again on the other side. So stereo A is still working. The funny thing is, it's still called stereo A for ahead, but it's actually behind us in the orbit now because it's going on.
Mhm. Wow.
So if you want to learn more about stereo and the satellites, there's a link on the page. So what are the characteristics of an aurora, like the Earth's aurora? The altitude above the planet. Helen was on board Sophia and could look out the windows and see the northern aurora, but she was still below it. But even though she was still below it, she was much closer than on the International Space Station, which is very much above it. So the aurora itself takes place about 60 miles up, unless it's a red aurora, which requires more energy, and it's about 200 miles up.
Okay, they don't touch the surface.
No, they do not touch the surface. The latitude, in other words, how far up and down on the globe the aurora shows up, is about 65 degrees plus or minus latitude. But if there's a huge coronal mass ejection and a lot of energy comes out, it can expand the aurora down to about 35 degrees, still not far enough for us to see it in Florida. So the colors of the aurora are based upon the oxygen and nitrogen in the Earth's atmosphere. Remember, the majority of the gas in the Earth's atmosphere is not oxygen, it's nitrogen. But because of the energy levels, we see more aurora in green than in other colors. The aurora may appear bright, but that's because people are using special cameras to take pictures of it that are low light. If you want to see, if you're ever up in the northern or southern hemispheres and you want to see the aurora, it's best to go looking for it after midnight. Kind of like if we wanted to see a meteor shower. You need dark skies. The density of the aurora varies with the energy level and the particles in the magnetic field. The aurora can go from invisible, it's just so low in intensity you can't see it, or it can be almost opaque. So if you get a very large discharge and it happens to go right down into a cluster of the magnetic field, you can get almost an opaque aurora where you can't see stars through it. But in general, the aurora is so thin and wispy, you can actually see stars through it. So for a while, we've said, if other planets are going to have auroras, they're going to have the following things. Otherwise, an aurora might not be possible. The planet's diameter. If you're too small, you may not have a magnetic core large enough to generate the field necessary to make an illuminated aurora. Okay, remember that. Planet diameter's got to be big. The atmospheric density by altitude. If the atmospheric pressure is too low, you may not detect the aurora. So you've got to have enough gas to be energized to make the aurora show up. Elemental content. Remember, our aurora is based upon energizing oxygen and nitrogen. If you're on a planet that has, let's say, carbon dioxide, you may not see the aurora because it might generate itself in deep infrared that the human eye can't see. So you have to, what kind of gases? If you want a visible aurora, it's got to be in those gases that have emission spectral lines in the range of human vision. Otherwise, you can't see it. The magnetic field strength itself, if the energy level is not enough to pull the particles down hard and fast enough, they may not produce enough energy into the gas to, fully excite the atoms into producing photons, or a sufficient number of photons. It may be visible, but it may be too dim to detect. And remember, not all planets have a north and south pole that are perfectly vertical. We've got some planets that are tipped over on their side. So their auroras may not actually be north and south. Their auroras may be east and west. So these are all factors that we thought were necessary for a planet to have an aurora. There was no mention of moons of planets having auroras or other things having auroras. I didn't throw in the videos. I just threw in some nice, pretty pictures. So this is the northern aurora as seen from the ISS. And you can see the swirling pattern of it. and you can see the bright and the dark and the low and the high density of it. In the low density area, you can still kind of make out that there's an Earth down below it. And you can still look over the edge of the Earth and see the atmosphere. So it's high up into the atmosphere. It's not down in the lower, denser parts. But this is up from ISS. So you can see not only do you have the green, but if you look at the top edge there through the center, you have the red.
You also have some orange on the limb. You can actually see some orange emission.
Yeah. Whenever you excite an atom, the amount of energy you apply to the atom to excite it dictates which electrons are going to move to what levels. And when they come back to their non-excited level, they produce a photon. And if they go out far enough, they'll produce a more energetic photon than if they're down low. So that gives you the different color, different energy levels of photons. So this is the southern aurora. And if you look, I don't know if you can make it out or not, but down in the bottom center, there's actually a boat there. So this is the aurora from sea level. And you can see that it has the greenish color. And there's a little bit of purple right at the top edge, but it's kind of hard to make out because you've got the plane of the galaxy also showing up in there. Now, both of these are kind of surface, and you're not seeing the entirety of the aurora. If you think the aurora is just what you can see locally overhead, no. This is the southern aurora as seen from high orbiting satellite. So the aurora actually wants to be circular. So it wants to form a magnetic circular ring around the poles of the Earth. And the brightness is, if the particle stream is coming in and it's denser on one side, it'll draw more particles down to make that part of the aurora brighter. Some are also saying that the reason why it's denser in certain parts of the aurora is because the Earth's magnetic field is not uniform. It's not, the same intensity of magnetic field all around that ring. If you have more field pulling on it, you can increase the density and make it brighter. So auroras are variable. They're not simple lines. They're glowy, swirly things. The Earth has a rotating magnetic core, and therefore this actually swirls. It's not just a fixed ring. But the reason why I'm showing you this one is, this is the Earth's aurora as seen from high orbit. Remember that? Here are two other planets in our solar system. These planets also have aurora. Their auroras are different colors. Their auroras, we can see them from high altitude because we send probes to Jupiter and Saturn. So we get to see their auroras at their poles, and we get to see this basic circular shape to them. That's why I showed you the circular one from the Earth, because if you were visiting the Earth from a distance, you would see the Earth's aurora like we see the auroras of Jupiter and Saturn. So the highest energy auroras are at Jupiter and Saturn. The Earth's aurora is small and weak by comparison, because Jupiter and Saturn are larger. They have higher density atmospheres, larger pressures. Their radiation fields are much larger. Saturn in particular is supposedly has a metallic hydrogen core. And if you compress and cool it down enough, hydrogen actually behaves like a metal. So it would give you a much larger magnetic field. So now let's get to the Martian auroras. We've recently had corroborating evidence from the United Arab Emirates HOPE spacecraft, which is orbiting Mars, confirming the presence of auroras around Mars. So Mars had previously been thought to have maybe at one time a moving molten core, but that was millions of years ago, and the core has gotten cold and solid, and therefore Mars shouldn't have an aurora. However, over the last about 10 years, the NASA InSight lander on Mars has received what is known as Marsquakes. So it's seismographs detect these vibrations about magnitude 4, not, planet shattering, but just periodic vibrations that are Mars quakes. And they've come to the conclusion that the only way you can have this without tectonic plates, sliding atop one another is if Mars still has some kind of molten core. May not be rotating, but it's definitely not solid. So supposedly Mars does not have enough magnetic field, because they thought the core was solid, that it had insufficient magnetic field to keep out the solar wind from eroding the atmosphere off of Mars into space. So not enough gravity also to keep its atmosphere from bleeding off into space. So Mars has a very low atmospheric pressure, and it's mostly carbon dioxide. However, the evidence we have is from 2 spacecraft. Their spectrometers on board their spacecraft, aboard the orbiting spacecraft orbiting Mars. One is NASA's MAVEN orbiter, and the other one is the United Arab Emirates HOPE orbiter. And both of these have the ability to detect UV. And the particular wavelength that they've detected is 289 nanometers. Not visual, it's in UV. And it's in the part of UV that just is on the edge of being not visible to human eyes. So even if we were looking at it, we might not even notice that it was there. But why are we just now noticing this? Why are we just now seeing these aurora? Because we didn't have the detectors to see it. However, in 2014, when MAVEN was in orbit, it detected what it thought were auroras, but there was so much long-standing science as to why Mars would not have auroras that it needed corroborating evidence before anybody would believe the observations of MAVEN. And when the UAE HOPE orbiter came in, it confirmed it. So now you have 2 corroborating observations, and well, I guess Mars has aurora, but they're in UV. So here's the evidence from MAVEN. The detector is specifically looking at 289 nanometers, and we'll get to exactly what that means. But the brightness is the intensity of the particular detector's sensors as it picks them up. Now, the satellite is orbiting Mars. So as you see these kind of diagonal stripe patterns, that's how it's orbiting Mars. So it actually took a number of orbits in order to get this data. And every pixel that you see there is kind of one snap of the sensor. And you can see that there are some areas of Mars that have brighter aurora than others. But the interesting thing here is there's no southern aurora. There's only a northern aurora. On the left side, you see latitude. 0 is in the middle, so that's the equator of Mars. You have to go up to 60 degrees before you have the aurora. And that's just like on Earth. You have to get towards the poles before you can see the aurora, which means the aurora on Mars is excited by solar wind hitting a magnetic field on Mars. So Mars must have sufficient magnetic field to produce an aurora. It's just an aurora that has so little energy. It's not really making it bright, but at the same time, the atmosphere of Mars is such that it's in ultraviolet, but that's not where carbon dioxide shows up. If you energize carbon dioxide, it'll show up in infrared, but this is in ultraviolet. So that's another question to ask is, why are they ultraviolet? So this is the MAVEN evidence. Here's the UAE HOPE evidence. Now, HOPE is not using a spectrometer, it's using a camera. It's a low light camera. So on the left side, you see that very glowy, sparkly thing. That's the daylight side of Mars at the time. And the satellite is moving across the terminator towards the unlit side at that time, the night side of Mars. And it's picking up the aurora as little bright splotches. So it's got individual aurora as opposed to a ring of aurora. So how can Mars even have aurora when the magnetic field is so puny? If you were to take the digital measurements, what you'd find is the Earth's magnetic field has a magnetic field strength, or Tesla, that's the capital T, rating of 4.5 times 10 to the minus fifth. Minus 5 is a very small amount, but the magnetic field on Mars is minus 9. So it's 1,000 times less. So the magnetic field strength on Mars is very puny compared to that of Earth, but apparently it has one. And apparently it's enough. And we know from InSight recordings that Mars quakes do occur. So Mars does have some kind of internal molten layer, but we don't know if it's molten rock or molten metallic, and we don't know if it's rotating or not. So this is more information we need. We have to send more probes to Mars to suss out the details. So even back when Mars might have had a molten core, it would have been a small enough magnetic field that couldn't keep the solar wind out. Well, we have an aurora, which says it's keeping some of it out. And Mars was supposedly small enough that its gravity could not have kept its atmosphere. Well, it's got some kind of atmosphere. Otherwise, what would you excite with the solar wind? So Mars's atmosphere is indeed very much lower than the Earth's atmospheric pressure. So how much of an atmosphere do you need, and what kinds of gases do you need in order to get an aurora? And how strong a magnetic field do you need in order to create an aurora that's detectable? So first you've got to ask, why are the auroras on Mars in ultraviolet? Mars's atmospheric content is 95% CO2, 2.6% nitrogen, that's molecular nitrogen, and the rest of it is down in the low weeds, which is argon, a little bit of oxygen, and carbon dioxide even less, not carbon monoxide, sorry. So those should have been in the spectral range, if it's carbon dioxide predominant, of the sensors we sent to Mars. However, when you send sensors somewhere, you send them for a specific mission or purpose. The spectrometers and cameras that we've so far sent to Mars have been designed to analyze rock and soil samples. They weren't really meant to analyze gaseous atmospheric emissions. So they were looking at things they could, put the camera right up on it, zap it with a laser, and when it blew the particles apart, find out what the emission and absorption spectra are to know what the material is in the rock. This is not a camera that's pointing up to the sky going, oh, look at the aurora. And also it's in the wrong spectrum. So they wanted to measure certain chemicals in the rock. So all the sensors, all the spectrographs and cameras operated in a certain range. So if we were looking for excited CO2 emissions, they would be in the 500 to 3,750 nanometer range, which is kind of green to deep red. UV wouldn't even be visible. The nitrogen spectra, if we're looking for those, it would be 550 to 950. Narrower, but still, green to red. If we were looking for argon is 740 to 860. So that's even deeper in the infrared. But what they found out was 289 nanometers. What would that be? Well, when you get up into the shorter wavelengths, the higher energy levels, you get more metallic elements like magnesium and zirconium. But those are too energetic. Those would be even less than 289. So maybe if the calibration and or the accuracy, the fidelity of the numbers aren't quite right, the 289 might be 303. If it was 303, that would be dead center on iron. So there is an emission spectral line for iron at 303 nanometers. Mars is well known for having iron in its soil. After all, it's called the red planet. Mars is also well known for having planet-wide dust storms, and they get to high altitudes that obscure the entire planet, where we can't even see the planet from orbit in space. So the dust gets very high into the upper atmosphere. And we know that Mars, even though it has low pressure, it has winds, and the winds carry these particles around the entire planet. So maybe what we're seeing is iron in dirt particles being lofted high altitude into the Martian upper atmosphere. And that's where they're being energized by particles from coronal mass ejections being directed by the weak magnetic field lines into these particles. And it's actually the iron that is getting excited and producing ultraviolet. But that's just a speculation on my part. We have to get more observations to find out actually what's going on. But that would say, why it's at 289 is it's actually skewed, and it's more likely to be iron than anything else. And iron.
Have you looked at the dissociation of carbon dioxide and having emissions of the oxygen in ultraviolet?
No, but I'll show you the information where you can look that up, because there's a wonderful website that will give you all the known emission lines. You can literally dial in a nanometer range and see all the lines that are available at different spectra.
It's just because it's ultraviolet, it smells like oxygen.
Yeah, but UV
But speculation on my side too.
UV has a wide range, and there are different lines for different elements, and they're all very, very narrow. So the particular range that they're seeing is 289 nanometers. If there was an oxygen emission line at 289, I would have said it's oxygen, but I didn't see one. We'll get to that in a moment. And here we are. It's a moment later. So what is it that emits at 289 nanometers? The US Department of Commerce and this wonderful organization called the National Institutes of Standards and Technology, NIST. I know some folks that work there. They have an online database that allows you to say, hey, I've got this spectral emission and it's at this nanometer level. What stuff is at that nanometer level? A nanometer is not a specific integer. If you go to even higher frequencies and shorter wavelengths, you can get finer resolution than nanometers, which means that 289 nanometers is actually, many more femtometers or attometers or picometers. So the NIST database measures it out to 3 or 4 fractional digits of a nanometer. That's how precise this database they have is. So if you went and looked in their database and said, it's 289, that's what NASA said it was, 289. I'll go look up 289. There is no spectral line at 289. So I said, let me spread the range a little wider here. How about if I go 289.0 to 289.05, and that returned 23 elemental lines. It's hard to read here, but you can see that's what it returned. It was 23 lines. If I opened it up to the range 289 to 290, it would return 424 lines, but none of them are precisely 289. So I'm going to say that the number that NASA announced, the 289, was not entirely precise. It was a ballpark based upon the particular excitation range and discrete values of their analog to digital converter, remember those, of their sensor. So if you have an analog to digital converter and the best it can do is resolution down to 1 nanometer, if the element you're searching for is actually a small fraction of a nanometer, one way or the other of 289, you can't tell it. You don't have the precision in your analog to digital converter to tell you that. So I'm going to assume that it's somewhere around 289, but precisely what it is, I don't think the NASA instrument has the ability to tell you, because that's not the reason why they sent those instruments to Mars. They were sent to Mars to look at sand and soil and dirt and rocks. And when you excite those with a laser or with UV radiation, they produce very bright, distinct line. And you don't need to get down into the 4 decimal digits of weeds of nanometers. You have nice, bright emission lines to see them. So if I were to look at these 23 lines, what I see is iron, thorium, chromium, technetium, manganese, titanium, sulfur, platinum, sodium, vanadium, uranium, and hafnium. But if I look at the soil analysis of Mars, the thing that has the highest percentage in that list is iron. And there's no oxygen in that list. So right around 289, there is no oxygen emission. But here's the link to the NIST site. So if you want to go, I go to sites like this and I could play for hours on end going, what's at this range and what's at this line, and and why is this next to that, and so you can go look at the spectral lines. Now these are the emission lines. They also have a database of absorption lines, so you can see both viewpoints of the spectral lines. So I'm going to guess that it's iron, and the only iron that you could hold in the atmosphere for an extended period of time is very, very fine particles of dust from the surface of Mars that have been lofted up into the upper atmosphere. So what are the available Aurora analysis instruments for Mars? So on orbit right now, on the Mars Reconnaissance Orbiter, there's an instrument called XRYSM. It operates from 362 to 3920. Has a little bit of UV, but it doesn't get down low enough. It doesn't get down into the 289 level. Lowest it goes is 362. On the ground, there's a spectrometer on the now these days deceased Opportunity rover. It had something called Minited that got down as low as 500, which is in kind of the green range, not UV. The spectrometers we've sent so far can't see down to 289. And the best way to describe that is, if the detector didn't detect it and couldn't detect it, it does not mean it doesn't exist. It just means it didn't detect it. So remember that whenever you see an instrument that NASA or European Space Agency says, hey, we've seen this, ask, okay, what's the spectral range of that instrument? And then what's the spectral fidelity or the precision of the measurement? Because if you're looking at things that fall between the integer values, it may not even see them. So always, whenever they announce something, look into the details of the instrument to find out what it can and can't observe. And we'll be getting into the Webb Space Telescope in detail as to what its instruments can see. There is a camera that can see in the near infrared that might be able to pick it up. This is the ChemCam. This is on board Curiosity. It is the camera they use to focus on the plasma coming off of rock that they ablate with the laser beam. So they point the camera at a spot on the rock where they're going to hit it with the energy of the laser beam to vaporize the rock. And when they vaporize a spot on the rock, it produces colors. And this camera becomes effectively their slitless spectrograph. It's like a color camera. And then they look at the colors that the camera picked up. And from that, they can decide what the mineral content is of the rock. This camera called ChemCam is on the end of the arm. So the arm has laser beam, and camera on it. That way they can get it close enough to get a really good image of it. Well, if it's on the arm, we already know the arm can do things like take selfies. We already know that they've taken pictures of Phobos and Deimos, the two small moons of Mars, as they orbit overhead. So we know they can take the camera and point it up at the sky. So the next time that HOPE or MAVEN detects UV auroras on Mars, tap Curiosity on its shoulder, because it wants to do new science too, because Perseverance is stealing all its thunder. Have it rotate the cam up at that part of the sky where they see the aurora, and see if from ground level on Mars that cam in UV can see the pattern of the aurora. So it won't be just individual spots. It'll actually be probably a slightly out of focus image of the aurora. That would be interesting. So why can't we detect the aurora on Mars from Earth? We've got the Hubble Space Telescope. It can see in UV. How come it can't detect it? Okay, on board Hubble, there is the COS sensor. It's a spectrograph. They call it, it's MAMA-based technology. It's a basically a bunch of holes into which individual light can go in. They're actually putting one of these kinds of spectrograph on the web. It can detect 115 to 205 and 170 to 320. Well, the 170 to 320, you've got a 289 in there. That's great. It could see it. The field of view of this spectrograph is meant to look at bright, distant stars. So its field of view is 25 arc seconds. That's very small. But Mars is small, so that's okay. It has 1024 pixels horizontal resolution. So the angular resolution of each pixel is 0.02 arc seconds. Sounds like you ought to be able to pick this up. There's another instrument on board Hubble called the SDIS. It can also pick up in the range of 289. And it has slightly larger angular separation of the pixels. It'll do 0.05. So why can't these see it? The angular size of Mars itself is only 3 to 25 arc seconds, which is, it's 3 when it's far away and it's 25 when it's closer in its orbit with the Earth. So if you said Mars is in its entire diameter 20 arc seconds across, and the aurora, you saw it in MAVEN, 1 pixel picked up 1 bright area. Would these two instruments on Hubble be able to detect that brightness? No. The most it could illuminate is 1 to 2 pixels in the entire spectrograph. So it's doubtful that these instruments would pick it up. So what we need is, the next time we send a lander or rover to Mars, we need it to be able to see in this range of UV, and we need it to be able to pick up dim enough UV to see the aurora, and then you'll have a picture of the aurora. The downside is the next 2 things that are going to be sent to Mars, the European Space Agency's FETCH rover, which is going to be going out and picking up all these samples that Perseverance is dropping off. The lander associated with that, which is sent by NASA, that's called the Mars Sample Return Program. They won't be arriving at Mars until 2028. But the FETCH rover will have 3 navigational cameras. It will have 3 navigational cameras on its masthead. I don't know if it's going to be UV inclusive or not. So in the interim, the best approach is the next time HOPE or MAVEN detects the UV aurora, have the cam on board Curiosity point at that part of the Martian sky if it's at night and see what you can see. If I knew somebody at NASA to send this to, I'd definitely suggest it to them. But it would have to be somebody on the Curiosity team. Let me see if I can find somebody on the Curiosity team. So Martian rocks. Well, if millions of years ago, when Mars did have a stronger magnetic field, and then it solidified the rock would have retained a magnetic field impression, which would be kind of like burying giant bar magnets in the soil of Mars. The magnetic field would not be moving and it would not be varying. So you'd have these fixed field magnets, but they would be stuck in the crust of Mars. And as Mars rotated, that's how you might get it. So if you think of a motor can either have a magnet at the core of it and a coil of wire on the outside, or it can have a coil of wire on the inside and a magnet on the outside. So depending upon what kind of stator you have in the motor, he decides where you want the permanent magnet, the non-moving part. So it could be that the aurora on Mars is because the rocks have an impression of the magnetic field, and it's actually the rotation of Mars within its own field there from the coronal mass ejection. So if the coronal mass ejection was the moving part, and you have the fixed magnets in the surface of Mars, and Mars is rotating, you can get a magnetic field. Now, you won't detect that magnetic field as a static magnetic field. It'll actually be a magnetic field that is only present when you have a coronal mass ejection. So if when we're making measurements of the magnetic field of Mars, we're doing that during a time when there isn't a coronal mass ejection impacting the atmosphere of Mars, we might not see a strong magnetic field. But if at the time the aurora is occurring, we did magnetic field measurements, we actually may see a stronger magnetic field on Mars. Just a thought. So we know that big planets with dense atmospheres can have aurora. We now know that Mars, which is smaller, has a lower density atmosphere and a much weaker magnetic field, has an aurora. What other things can have auroras now that we've dispelled the big size, big atmosphere, big magnetic field postulates? Turns out, remember this comet that we sent a probe down to? Well, European Space Agency did. Just call it 67P. Well, we actually caught an aurora coming off of it. Now, at the time, it was not behaving as a comet because it was too far away from the sun. So what is all this glowing stuff? This glowing stuff it has an aurora. But it has next to no atmosphere and it's rotating, but it obviously doesn't have a molten rotating core. So if the rocks of 67P actually had a magnetic impression from whatever parent 67P was comprised of, then the rotating object with a static magnetic field within a coronal mass ejection impacting it could produce a larger magnetic field. So even if it had a very tiny atmosphere, you could have an aurora. But since we only had one spacecraft go take these pictures, yes, we've got evidence that it might have an aurora, but we need to send another spacecraft there to confirm it. Now, the magnetic field of 67P is 10 to the minus 8, which is greater than Mars, but still far less than Earth. So as we do more observations, our baseline rules as to what things can have auroras, they be changing to smaller values. So we've confirmed that Mars has an aurora in UV. It could be that magnetic field of Mars is actually static, and it's the rotation in the solar wind that excites the particles. Or that Mars actually does have a molten magnetic, metallic core and it's rotating. We just haven't discovered that yet. Or it could be that the minimally required magnetic field strength for a body to have an aurora is thousands of times less than the Earth's magnetic field. So dial it down and give others the chance to have an aurora. And that the atmospheric density needed to produce an aurora is thousands of times lower atmospheric pressure than that of Earth. So far fewer molecules to be excited. And that maybe it's stuff that's particulate in the atmosphere as opposed to gases in the atmosphere that you need to look for, but you need to start looking for auroras and other than infrared or visible light. So here's a question. Earth's auroras are swirling because the Earth has a molten metallic moving core that produces varying magnetic field lines as the Earth rotates. So if Mars's core is solid, then the magnetic field lines should not be moving. And if we do get a video of the Martian aurora, it should be more or less stable, not swirling, but it could vary in brightness. So it wouldn't be sort of this flowing thing like it is on Earth. It would be just bright and dim, pulsing. It wouldn't be swirling if the magnetic field is stationary based upon an impression left in the rocks of Mars as opposed to a moving metallic core. So as I was saying, based upon motor design, you can have a magnet on the inside and a coil on the outside, or you can have a coil on the inside and a magnet on the outside. And you know which one is actually moving. So the thing we need to do is send more instruments to Mars that are specifically designed to look for aurora from the ground up and in a broader range of wavelength. Any questions?
Nope.
I have 10.
Yes, go ahead.
Okay, so there's people that speculated about auroras on these other items.
Yes.
And my thought is, and I hope it's not a long one because I have 9 other questions, that why did they speculate before they went? I mean, what was it about auroras that they needed to know to help with science? I mean, that they had to go out there and hypopulate, and it seems like they got it all wrong. So I hope they're all dead. Not that I want them to be dead, but you know.
Here's two things to know about science. The first thing is analogy. That is, we know how things happen on Earth. We've decided, postulations and maybe facts as to, the history of the Earth and such. And now we want to look at other planets, other objects, and say, how do they compare to what we know about the Earth? So the Earth has an aurora. Do other planets have aurora? Hey, look, Jupiter has an aurora. Saturn has an aurora. So we know big planets with atmospheres and large magnetic fields, those are the ones with auroras, because that's all we know. That I refer to as scientists with the blinders on. So the only observations I have are these of the Earth, those of Saturn, and those of Jupiter. Therefore, the only things that can have auroras are big planets with large magnetic fields, dense gaseous atmospheres. Check, you can have an aurora. They denied everything else auroras based upon our understanding of the Earth as compared to Jupiter and Saturn. So if they only see that, then they think only that can have an aurora. And now what we're finding out is there are other ways you can have an aurora, and they don't have to be big planets. They can be, asteroids and comets. They don't have to have enormous magnetic fields. They can have very weak magnetic fields. In fact, their magnetic field can even be static as long as the is rotating.
So in a sense, they were looking at these other planets that they could see that had auroras, and they figured those planets have a magnetic field. Mm-hmm. And that's what they were interested in knowing by the aurora?
No, they're just doing compare and contrast. So we know.
Okay, so it wasn't looking at for any kind of reason for looking at auroras, particularly.
Radiation levels, magnetic field strengths, and radiation levels. So we know that the Earth has a magnetic field. We also know that the Earth has these things called the Van Allen belts. Those are belts of radiation. If you remember when I was discussing satellites, there are low Earth satellites, there are medium Earth satellites, and there's this big gap. And then you have geostationary satellites. How come we don't put any satellites in there? Because that's where the Van Allen belts are, and the radiation would cook the satellites. So there's a gap. Well, do other planets have radiation belts? Do other planets have magnetic fields? Do they have auroras? Because if we can detect an aurora around another planet, we know that planet must have a gaseous atmosphere. It must have a magnetic field, and it might also have radiation belts. So we're comparing apples
Okay.
to hopefully apples. And what we're finding
Okay.
out is the thing that we're comparing, auroras, can be on more than apples. You can have grapes with auroras.
Right. Well, it was much more interesting to say we're looking into auroras than to say we're looking into the radiation on another planet to compare to ours.
No, we are.
So-
We're definitely looking at the radiation because
I know that's what you're saying is that came out of this aurora thing is what the radiation is also included in that. But
Well,
when you talk to other people to get their interest, it's better to do it with an aurora. And that was my other thing
Well,
is
yeah,
if I
there's
make
that.
it to Mars and I'm standing on Mars and now I'm looking for this aurora,
You won't see it because it's in ultraviolet.
I won't see it at all.
You won't see
No
it at
matter
all.
what. And will it be occurring like it does on our planet that it comes once in a while?
Yes, and it also occurs at northern latitudes. But for whatever reason, there's apparently no southern latitude aurora on Mars, or they haven't detected it yet.
Or they haven't detected?
I have not detected because you have to remember that it's easier when there is more atmosphere. And then the atmospheric pressure, when you have the areas on Mars, they're on the summer side, on the heated temperatures, the density of the atmosphere diminishes. And then where you have the winter, so it depends how hot it is, which latitude you are, and then you would have more dense atmosphere. It happens here too. So
But
you have like the
that's all.
summer is less dense.
That's also
Why is it,
that's
why
also
isn't it visible?
that's also presuming that it's the gas in the atmosphere that is being excited, producing the ultraviolet aurora. If it's actually iron particles lofted in the upper atmosphere, then the atmospheric density could be very light and you could still have an aurora. But the aurora is only seen in ultraviolet. And since the human eye cannot see in ultraviolet, you need specialized instruments to see it in ultraviolet.
And why is it in ultraviolet? And it's not in ultraviolet here.
No, it's because the Earth's atmosphere is the thing being excited by the coronal mass ejection particles. And when you excite the Earth's atmosphere, you're exciting oxygen and nitrogen, and the oxygen is producing that bright green color. Mars does not have that high a level of oxygen. It's mostly carbon dioxide, and the excitation of carbon dioxide produces infrared.
No,
So
ultraviolet.
Well,
Infrared, yeah.
the question
but
is,
if,
how come they
Yeah.
don't see an aurora in infrared?
Might not have the right instrument too.
No, but they do. They have infrared cameras that can see from near infrared down into mid infrared. So if anywhere in there were excited gaseous molecules like CO2, then they would see it, which is another way of me saying, I think it's the iron particles in the atmosphere that are actually being excited. That's why you only see the aurora in UV, because when you excite iron, you're not going to see emission bands in in infrared. You're only going to see them up towards the upper end of the spectrum.
The thing is that for you to, it could be some molecule with iron, like
Yes.
iron oxide, but I don't think there is enough energy to excite them in that way. I'm not sure. I'm gonna take a look of it because it's when it's something solid,
Mhm.
it's very hard for you to excite. It needs to be a gas.
Well,
so say that we're going to go to Mars, right?
yes.
And we're going to be taken along oxygen. And we're going to be introducing oxygen to this planet, right?
No. We're not
recycling
going to be
the material.
we're not going to be terraforming the planet and putting up enough oxygen for you to see it.
Oh, darn. It would be a very entertaining thing. It'd draw a lot of people to Mars for the
You
entertainment
watch too
portion.
much Star Trek.
No.
We're going to find out it's something extremely convoluted, like iron in the dust particles gets lofted in the atmosphere only during the seasonal months that you have large dust storms on Mars, and it gets up just high enough that it's actually X-rays that are bombarding the iron particles and causing the aurora. So if you
No,
don't have
this
the
is
right,
gonna be, and my bet is some molecule. It could be a dissociated molecule, an ionized molecule of a gas. I don't think it's something, because it's a basic, the sand is silicates, so silica oxide and iron oxide. So you need very high temperatures for you to ionize, those minerals.
it doesn't have to be high temperatures. It has to be high energy levels, which is indirectly temperature. But if you have small enough particles and you have energetic enough X-rays in the upper atmosphere of Mars, you can do that.
So if Helen and Monroe, hello?
Yes.
If Helen and Monroe got together and wrote up this hypothesis of this iron in the atmosphere and how it's causing this aurora effect, could you propose that to the scientific community? And maybe they would you would come out right.
Actually, the best approach would be find a person on the Mars Curiosity rover team, because they're the ones that can control ChemCam. And right now, the Curiosity team is kind of idle because Perseverance is getting all of the hoopla because it's the newest, latest thing on Mars. So if all they had to do is say, okay, the next time MAVEN and HOPE both detect aurora in the atmosphere of Mars in UV, move the ChemCam around so it points at that part of the Martian sky and have it take a picture, because it can see in UV. So if it can see in UV any sort of glowy, patterny thing, it becomes a new observation by Curiosity, and that means that Curiosity will steal the marketing hype PR away from Perseverance, and I think they'd want to do that.
Yes, I would think so too. And I think you guys could write up a recommendation to them and get
no.
credit.
You don't have to get that sophisticated. All you have to do is find the right person on the team, get their email address, and go, hey, I hear that MAVEN and HOPE have spotted an aurora on Mars in UV. We don't have any spectrographs that can do it at the moment, but you guys have ChemCam on board your Curiosity. The next time that MAVEN and HOPE spot the aurora, could you guys like pan ChemCam up to that part of the sky at night and see if it can capture the aurora? Because that would be a new and interesting observation, and see if they go run with it.
Well, couldn't we take part of this video and send part of the video and say, this is what we want you to do?
No.
No, we have a few contacts that might have the correct context, like
Oh, okay.
like not even the 7 degrees of Kevin Bacon. Maybe
No. I'd go looking for the person responsible for the ChemCam observations on Mars on the Curiosity rover. Find that person's email address. They're probably sitting around looking for new things to do to steal Perseverance's thunder, and this would be just the ticket.
Yeah.
I think so. It's great. We heard it here first. Now, my thing is still going back to the fact.
What was that, Helen?
Are they in JPL?
Yeah.
Okay, in California.
Actually, no. I take it back. They're not at JPL. They're at Johns Hopkins.
John Hopkins. So who we know that is in John Hopkins?
Oh, it's easier than that. Come on.
Dana Bachman might have the
No,
contact.
no.
No?
Quit with the
Okay.
Kevin Bacon 6 degrees.
Okay.
Here,
Cool.
here's a reference for you.
Twitter?
No,
We
here's a
go
reference for
directly
you.
on Twitter?
No, here's a reference for you. Go right through Falcon's Maze. Nobody?
What?
Nobody?
Ooh,
Go right
no.
through Falcon's Maze? Oh, come on, Matthew Broderick.
Okay, I don't know.
A movie from the 70s?
Oh, with Rutger Hauer?
No.
Give
Yeah,
us
he was
another
the
clue.
guy.
Matthew
Another clue.
Broderick was a teenager and he had a friend who was a scientist. His friend scientist went missing. And what they found out was his friend scientist created a supercomputer called Joshua, and Joshua was given responsibility for the US nuclear missile fleet.
War game.
War game. There you go.
Eileen.
Eileen wins the mythical prize. Yes.
Yay. Okay.
So in war games, they were trying to figure out how to find Dr. Falcon. And they were
Oh.
playing these computer games and they said, how do we find Dr. Falcon? He has this computer game that's a maze. And what you do is you go right through Falcon's maze. Basically, if you win the maze, you will get the notoriety of the guy that developed the maze, and therefore you can contact Falcon directly. So go right through Falcon's maze. So in this case, what you need to do is to identify the individual at Johns Hopkins Applied Science Center that is responsible for the ChemCam instrument. Get that email address and go right to them. Forget all the other stuff. Go right to them and just like a
The
little one
principal
paragraph.
investigator.
Well, not the principal investigator for curiosity. This
No,
is the person.
that is a principal investigator for each instrument.
Yes, it's the principal investigator specifically for ChemCam. Find that person and then shoot them a little paragraph like a, hey, connect the dots and see if they take the bait. And if they take the bait, a month or so
You
from
don't even
now,
need to hear the hypothesis. Just point the spectrograph and see if you can get something. And then whatever comes.
ChemCam is not a true spectrograph. It's a color camera. It's a wide spectrum color camera. So
With
it produces spectra, but the way it produces spectra is by taking a color image and then doing a Fourier transform on it to show you like, not a picture, but it flips it and then says, here's the buckets for all the pixels based upon their energy level. And the amplitude is how many of those pixels you saw. So,
Isn't this a hypothesis that you're having? Isn't this just like these other guys that got shot down that said that, oh, there's no Aurora anywhere else?
yeah.
Now,
But
this
they were
is the
doing
same
that. They were doing that based
I don't
upon.
think there was someone saying that is no auroras. It's just like, imagine like you could see something and then you think Earth or everything you see around looks like the way it is because your brain gets used to. And then by the point that someone gives you your glasses and then you see better, you have a better instrument to look at nature. You start figuring out things. It's not that someone postulated that's impossible. It's more like that's what we knew. And so that's what we use as analogy for we expect to see somewhere else.
But there was somebody that came up with that, right? Nobody came to them and said, oh, please write up an analysis, right?
No. I could almost guarantee you there were scientists at NASA that believed that Mars could never have an aurora because it has too weak a magnetic field and it has too low an atmospheric pressure.
Right.
And they will state that as the boundaries because they had their blinders on. That's all they know is big planets with big atmospheres and big magnetic fields, they can have aurora. Mars, no, it doesn't have a strong enough magnetic field. Its atmospheric pressure is too low. And, they
but now, isn't there an opportunity now to write up a new type of, I guess you called it a hypothesis, right?
Yeah.
That they were they were thinking that this was happening. Now, what you're telling us about this iron, we don't know for a fact, but since I believe in
Of
more,
course not.
that's
an hypothesis.
Monroe, and I believe in Helen, I believe it's fact,
No, it's not fact. It is a hypothesis.
but I know it's not. And I'm thinking, why not write up one of these recommend, and then you could be right, and wouldn't that be nice to be recognized for it?
If you want to publish, you have to be a part of the scientific click community. So
you're saying it doesn't matter?
Doesn't matter. If I was to write up a postulation regarding the source of the auroras on Mars, who would I send it to? How would I get it published in a noteworthy scientific journal? It would be stopped by the peer reviewers and go, that's not science fact. We only publish peer-reviewed science. So I would have to have the observations that I don't have the instruments to make.
Well, Monroe.
Yes.
So the first idea is to find the right person to convince them if they can do the observation.
Yes. Adam?
Well, Monroe, as we discussed earlier today, you could publish it in the Wall Street Journal. On the other hand,
they'll publish anything.
Yeah. On the other hand, I just happened to have watched a video put out by Fermilab yesterday, I think, and the process for getting something proposed and done takes about 6 or 7 years. And
if you're lucky.
I was just going to say that. And 2/3 of the things that they qualify, they just say, we can't prioritize it. We don't have the time and money. So, so Monroe is absolutely right. You just find out who's working on the ChemCam control team on the rover, and just mention to them all they need to do is turn the instrument to actually get it as qualified science and get it done is 7 years or so. And then they have to get a whole team of scientists to analyze it. And then it has to be done within 3 years. And if it isn't done within 3 years, they need to have another team of 12 scientists analyze it to make sure it's still topical and stuff. So I think Monroe's got the idea there.
You want to know here's the second shortcut. Do you think there might be a ChemCam type camera on board the mast arm of Perseverance?
Sure, second observation.
Exactly. NASA's not going to reinvent the wheel. If they want to do spectroscopic observations of minerals by blasting a rock with a laser, they're going to carbon copy whatever they did on Curiosity and mount that on Perseverance. And I haven't looked for it yet, but it wouldn't surprise me to find that there's a ChemCam on board Perseverance as well. So if I can get the Curiosity ChemCam team excited enough to point their camera at what might be the Aurora and take a UV snapshot of it, if they get an observation that has any detectable data, they're going to go tap on the shoulders of their friends over at Perseverance land and have them do the same thing with their ChemCam. And now you have 2 corroborated observations, and it's peer-reviewed science. So
yeah, they need to find some real data with Curiosity, because right now at this moment, Perseverance has a huge list of priorities of the observation. So it's like it's the new kid on the block, so everybody wants to interview the kid. So it's the line of scientists asking for proposals, and the people who are working are busy right now. So only if it's something really cool that they would stop what they are doing to actually do the observation.
You also have to know the social nature of the team on a particular spacecraft. So if I out of nowhere came up with a suggestion for the ChemCam for Perseverance, it would just basically be ignored because it's too deep in the weeds and would be too disruptive. They're probably not happy with the fact that the Ingenuity helicopter is stealing some of Perseverance's telecommunication time for science.
Oh, yeah.
So they would not be willing to let some interloper in from the outside. However, if Curiosity spotted something new, there would be new things that Perseverance might take a look at under the right circumstances they might be able to sneak that into the laundry list without much perseverance because it's going to be at night. And it's only going to be when MAVEN and HOPE spot the aurora. So it would be a very narrow point in time, and it would be almost like push the button, have it rotate around, take a picture, go back to its main job. So they could, you know, within a few hours, get the information they need to compare it with Curiosity. And the Curiosity team would go, we saw it first, we saw it first. And the Perseverance team would go, new science from Perseverance. So nobody would mention the lowly little amateur scientist that actually said, A plus B equals C. Do you connect the dots?
Yeah,
So
that's a shame though, isn't it?
no, that's just human nature. Come on. I'm not going to be messing in their bailiwick. They're not going to listen to what I say.
But there's a lot of people out there that have probably introduced thoughts that
yes.
went up the chain, but they didn't get any credit at all for it.
Oh, it's
That happens all the time.
I guess you can say it's more distressing than that. There are people out there that have an idea that don't know how to flesh it out, don't know how to go and find, hey, there's an aurora on Mars. Cool. And then they're done. They don't go, well, they never mentioned that before. Why all of a sudden? Oh, well, here's the data. It's from HOPE. It's from the United Arab Emirates HOPE. Well, okay. Well, don't we have to have something else look at it too? Yeah, MAVEN looked at it in 2014, but that was just one. Now we have two. So now we have confirmation that it exists. And then we have confirmation of the particular spectral band that it's in. Okay, cool. And they never dig down deeper because I've got that, you know, disgusting polymath mind of mine. And if it doesn't get out of my way, I'm going to go study it. So I studied it and said, well, let me go find it, because I went looking for spectral lines. How do I find what's the emission wavelength for 289? I had to go find a database. People are giving me like these cool pictures, and all the pictures are showing me visual spectra or infrared spectra. I want something up in UV. Closest I get was stuff that was up in X-ray. No, this is UV. Don't we do any observing in UV? And then I find out, well, most of the instruments that we've sent so far don't. And, you know, all along that path, I could have been disenchanted from carrying it on any further, but not that I believe in astrology, but I'm one of those stubborn Capricorns. And nope, the polymath plus the Capricorn, I'm going to dig deep enough where I can find data. And once I find the data, if the dots have not been connected, I'll postulate and see if we can't connect the dots. And now it's time to go find someone who is part of the program, not part of the problem. So I'll, you
Okay.
know,
So are you saying that you already thought of contacting someone to turn around the machine to look at this already? Or did we brainstorm this tonight?
No, I brainstormed ChemCam earlier this week and said, you know, I need to find out who on the Curiosity team is responsible for ChemCam. And let's see, Curiosity is under operational control of not JPL, it's Johns Hopkins Astrophysics Institute, because NASA JPL can only handle so many craft at one time. So Curiosity being ho-hum, it's Curiosity, it's older, you know, they farmed it out to Johns Hopkins. And so that's where the person would
tried to get into this already to let people know that this is a thought.
Yeah, I'll probably send out an email in the wee hours of tonight.
Yeah, but you've been thinking about doing this all along then.
I've been thinking about using ChemCam for this earlier this week when I found out what the spectral response range was for ChemCam. And I said, it's the right kind of camera. It's just pointed down at where the laser is so it can do, you know, mineral analysis spectrometry. But I remember that same mast on the Curiosity pointed up at the sky, looking at the moons of Mars. So it can point up at the sky. So why can't we get them to point it up at the Aurora?
Mm.
So like I said, I'll spend probably 2 hours formulating a nice, concise email, as terse as possible with me, to just get their attention and see if I get a response back.
That's exciting. That's exciting to know you're doing that. And it's also interesting that you said that it was turned upside down and it could look up. And I remember last week you had a little thing in the background.
Yeah.
Your camera that can look, you were going to try and turn it upside down so it could look up.
Yeah, it's still here. It's off to the side.
Oh, did you get any further with it?
Because it's actually on the network, I put a cover over it. Here, I'll slide it back in where you can see more of it. It's just on a little piece of plywood.
Your little friend.
My little friend in the back. See, it's got a little cover on it.
So did you get any further with it? Because it's going to go outside, right?
Yes, but this is the temporary mount for it, so I can do testing of the driver and such. But I'm going to have to take some pictures of things. And what I'd like to get pictures of are Saturn at closest approach. And I'd like to get pictures of Jupiter and the moon and all kinds of stuff like that. I'd like to get pictures of the Orion Nebula, but it's the wrong time of the year. So if I wanted to take a picture of the moon tonight,
Analemmas.
I can't get that far. That would take a year. If I wanted to take a picture of the moon tonight, the moon's set at 3 o'clock this afternoon. If I want to take pictures of Jupiter and Saturn, I have to be up at 3 o'clock in the morning. And as I've already mentioned, this weekend, I'm in the online sessions with the Society of Amateur Radio Astronomers, SARA, and their session started this morning at 8 a.m. So I've been up since about 7 a.m. And once we get done, I'm unless I go eat some energetic food, I probably won't be up at 3 a.m. And tomorrow's session with the radio astronomers starts at noon. So I have to be awake for that.
You have a busy weekend.
It's amazing how busy somebody retired can be.
Yes.
I hear you.
Okay, any other questions or comments regarding Martian auroras?
No, just they are cool.
Okay,